Alright, now let's go through some wave phenomena. So I'll be using the example of a string that is free about both ends. So if I give this string a flick on the left-hand side, it'll send a wave pulse to the right, and because it's allowed to move on the right-hand side, this wave pulse will be reflected back. And your question might be, well, what if I quickly give it another flick and send another wave pulse down? And the answer might be quite surprising, actually. So what happens is we can sum the contributions of both of these waves as they overlap. So these dotted lines are the wave contributions. And so while the contribution from the purple wave is 0, then what we observe is just the orange wave. And same thing on the other side, what we observe is the purple wave. So since these waves have only just started to overlap, they are mostly expressed on the outer edges. But towards the middle, they actually add together and we might get a little bit of a bump. Now that's obviously exaggerated quite a bit, but you get the idea. And when they are completely overlapping, we get something much taller than either individual wave could create. And then what happens is they just continue on their merry way as if nothing happened. And this phenomenon is called constructive interference. Now, if I go ahead and tie a knot in the right side of the string, then what happens is the wave is actually reflected and it comes back upside down. And so your question again might be, well, what if I send another pulse quickly down so that I've got one moving to the right above the line of the string and one moving to the left below the line of the string? And the answer, you can probably see where this is going, is that this time, because the waves are on opposite sides, we're going to subtract the purple wave's components from the orange wave. So over here, while the purple wave is 0, we will see most of the orange wave. And while the orange wave is 0, we will see most of the purple wave, because these have just started to overlap. But in the middle, we get this kind of shape. And when the waves overlap a little more significantly, the shape that they make is quite smaller, until finally they're overlapping completely and they cancel each other out completely. And then, just like before, the waves will just continue on their way. They only interfered with each other temporarily. And by the way, this is called destructive interference, because the waves look like they destroy each other for a short period of time and the string is just still. Now, what happens if I fix this string at both ends and I give it a bit of a pluck? So it could be a guitar string or a harp or a violin or something like that. And by plucking the string, I'm going to send wave pulses in both directions, up and down, left and right. And if I keep sending waves down the string in this manner at just the right frequency, I can create a really interesting phenomenon called a standing wave, where instead of appearing to travel, the wave actually looks like it's anchored by these points here that actually don't move. So I've drawn this standing wave at various points in its cycle. And as you can see, and these points on the end as well are also examples of this, none of these points are actually moving up and down. They look like they are staying still. And these are called nodes. Meanwhile, the regions of the string between the nodes are oscillating up and down. So it starts off quite tall, gets smaller until we see it completely flat, and then turn around the other way. So these points, and by the way, fixed ends, as you can tell, are always going to be nodes. And the regions that look like they're moving, well, they're called anti-nodes. They're just the opposite. And this phenomenon is called a standing wave because it looks like the wave is standing still and just shaking up and down. Now, if I keep on varying the frequency, I'll be able to introduce more and more nodes as I increase the frequency. And we call these harmonic levels. So this is the first harmonic. This is the second harmonic. This is the third harmonic as well. And harmonic levels are related to the wavelength as well as the length of the string. So we can write this for strings that are fixed at both ends. Lambda equals 2 times the length for the first harmonic. Lambda is the length for the second harmonic. Lambda is 2/3 of the length for the third harmonic. And in general, we can just write that lambda is 2L over N. So again, this is the wavelength in meters. This is the length of the string in meters. And N is the harmonic number. And N is actually unitless. Now, if I go back to my example where one end of the string is free to move about, then this will always be an antinode. And this actually means that we will never see the full periods of these waves being expressed. Yeah, only fraction multiples of it. So if this is the first harmonic for a wave that is fixed at only one end, we have lambda equals 4 times the length. And as you can see, if the string was longer, this is where the rest of the wave would be. This is the third harmonic, and we have lambda is 4/3 of the length. This is the fifth harmonic, where lambda is 4/5 of the length. So in general, we have lambda is 4 times the length over N. Again, this is for strings that are free at one end. And if you can't wrap your head around how exactly these kinds of shapes could be produced, just think that you are holding this free end and shaking it up and down. And what you observe up to the point where the string is tied down are these harmonic levels. Now, this whole harmonic thing is a direct consequence of the constructive and destructive interference that we just talked about. So over here, there could be two waves with a positive component, and over here, there could be two waves with opposite components that cancel out. And the thing is, if we get the frequency just right, these will all be happening simultaneously. That's what makes it such an interesting and rare phenomenon. And by the way, it doesn't just happen with strings. It can happen in wind instruments, and it can happen in just everyday pieces of metal, like bridges or houses or bigger structures, which is called the phenomenon of resonance. Resonance is where the oscillations that you input into a material match that material's fundamental frequency. And this can actually lead to some really horrible engineering nightmares, like bridge collapses if the wind is coming in at a certain frequency. So it's something that engineers have to be very, very mindful of when they're designing structures.